The quantum phenomena of light can be explained without photons, on the basis of electromagnetic waves. A light wave is a combination of electric and magnetic fields in the form of an electromagnetic wave. An electromagnetic wave does not have the shape of a line or a plane, it has a three-dimensional shape. So, what is the shape of an electromagnetic wave? What is its length, width, and height? If we cut the electromagnetic wave into slices 1 wavelength thick, we get disks. One electromagnetic wave takes the form of an electromagnetic disk with a thickness of 1 wavelength. An electromagnetic disk consists of an electric and a magnetic field. The forces of the fields act on the electromagnetic disk and thereby shape it. The force of the magnetic field acts in the direction of contraction of the electromagnetic disk, while the force of the electric field expands it. The diameter of the disk is a balance between the repulsive force of the electric field and the attractive force of the magnetic field. The fields of an individual electromagnetic disk may contain more or less energy. The diameter of the electromagnetic disk depends on the energy of the wave. The diameter is such that the amplitude of the magnetic field density is always the same. The frequency of the wave is not important. An electromagnetic wave can enter circumstances where a light wave loses its energy. The electromagnetic wave enters the depths of the sea and loses energy along the way. When energy is lost, the amplitude of its electric and magnetic fields does not change. Only the diameter of the electromagnetic wave decreases. The light wave should travel through a selected point in space. At this point, the strength of the electric and magnetic fields changes according to a sinusoidal function. By changing the strength of the fields, the energy of the fields at that point also changes. According to the law that the energy of a closed system must remain constant, the energy at this point cannot change if no energy enters or leaves the point. According to Ampere's law, electric and magnetic fields in the direction of the pointing vector create a displacement current. At the point, the energy of the electric and magnetic fields is exchanged with the energy of the displacement current. The total energy of the wave, that is the energy of the electric field, the magnetic field and the displacement current, is always the same at the observed point. The diameter of the electromagnetic wave, that is the disk, is measured by directing the beam into the double slit. Interference lines appear behind the slit when the same electromagnetic wave enters both slits. The diameter of the electromagnetic wave is measured based on the adjustment of the distance between the slots. Sometimes a light wave meets an electron. The volume of a single electromagnetic wave is at least 1 billion times larger than an electron. A light wave sometimes knocks an electron out of an atomic shell. The brightness of the wave, that is the diameter of the electromagnetic wave, does not affect the ejection of electrons. Electron ejection cannot be affected by the amplitude of the magnetic field density either, since it is constant, regardless of the brightness and regardless of the frequency of the light. Rapid changes in the magnetic density of an electromagnetic wave knock an electron out of an atomic shell. When the magnetic density amplitude is always the same, the maximum slope of the magnetic density changes is linearly proportional to the light frequency. The energy transferred by an electromagnetic wave to an electron can be written using Planck's equation. The properties of light can be understood and fully explained by electromagnetic waves without a photon.